In example 3, they want us to approximate the area for another quadratic function. So we have an inverted parabola, and they want us to use the closed interval from 0 to 3. And we're going to be using midpoint heights with 6 subintervals. Alright, so let's overlay this with our rectangles. And the first thing that we want to do is to determine what our delta x's are. So let's calculate those. Delta x is equal to b minus a over n. b is 3 minus 0 over 6 is equal to 1/2. We're also going to create a t-table just as we've done before for x and f of x values. So what are the x values that I'm going to be using? Well, it's going to be 1/2 times the width of the rectangle plus my previous x value. So in this case, my previous x value is 0, and half of 0.5 is 0.25. So 0.25, and then the next one is 0.5 plus another 0.25 is going to be 0.75. And so we're going to be increasing by 0.5 each time. 1.25, 1.75, 2.25, and then finally 2.75. So those are the x values that correspond to the midpoints of the rectangles. Now, so we will go to our graphing calculator, put this function in for y1, and you can set your delta x to be 1/2 so that it increments by 1/2, and use your table function to generate your f of x values. Or you can do them one at a time, but in any case we get, and I'm going to use 4 decimal places. So we want to report 3 decimal places on the AP exam, and to do that we typically want to carry more than 3 in our calculations. A good rule of thumb is that if you carry 5 decimal places in your calculations, then you'll definitely have 3 in your final answer, regardless of what your operation is. And so you could end up taking the square root, or really anything like that, sine, transcendental functions, natural log. You'll be okay. You'll have 3 decimal places of accuracy. But in this case, since we're just adding and multiplying, I'm going to carry 4 decimal places, and that should be sufficient. Just don't have the room for 5 decimal places. So 3.9375, and then the same height again, 3.9375, and then for 1.75 we have 3.4. 375, 2.4375, and finally for 2.75, 0.9375. Alright, so our midpoint Riemann sums for 6 subintervals will be equal to 1/2 times, and so in this case I've got 1, 2, 3, 4, 5, 6. All 6 of my subintervals, and I have a midpoint for each one of those. So this is minus the confusion of, okay, wait a minute, it's left hand limit, so which one do I not use? It's a right hand limit. So we don't even really have to worry about that now with midpoints, and we're also getting a more accurate Riemann sum. So we're going to put in all of our f of x values. Alright, and calculating this, we get 1/2 times 18.125, so 18 1/8, and this is going to be 9.0625.